Your brain doesn't preserve memories like computer files. Instead, it constantly reshapes them. Stress hormones don't erase memories but alter their recall. Within 6 hours of stress, cortisol modifies synaptic connections in the hippocampus. Contrary to common belief, stress isn't just a memory killer. It can enhance memory by focusing the brain on relevant details. Researchers from the University of Buffalo found that under acute stress, memory retrieval improves for emotionally linked events. But chronic stress has the opposite effect, shrinking hippocampal volume by up to 8% as seen in MRI studies. Such stress-linked neuroplasticity changes your brain's architecture over time. Many believe multitasking boosts memory. Yet, research shows it does the opposite. Stanford University studies reveal multitasking decreases short-term memory by taxing the prefrontal cortex. This area coordinates the transfer of information between brain regions. Within minutes, constant task switching increases mental fatigue and decreases cognitive control. Neuroimaging reveals reduced gray matter density in the anterior cingulate cortex, a region vital for error detection and memory encoding. Surprising. Dopamine release, vital for memory consolidation, drops when multitasking, according to a 2012 study. This inhibits deep learning processes, making information retrieval less efficient. Memory myths often omit the role of sleep. During deep sleep, the brain performs remarkable cleanup, removing waste proteins like beta amyloid. This isn't just housekeeping. A 2019 study showed that sleep deprivation reduces hippocampal neurogenesis by 50%, impairing memory formation. Slow-wave sleep enhances memory consolidation by boosting neural communication. Calcium channels in the thalamus synchronize to stabilize new memories. Sleep's effect on memory isn't about quantity alone. Quality matters too, as REM sleep facilitates emotional memory processing. Without it, emotional regulation falters and recall becomes less reliable. The myth of photographic memory implies fixed recall capabilities. In truth, memory is more reconstructive than reproductive. Each recall modifies the original memory trace. Harvard studies show that each retrieval alters the strength and content of memories. The hippocampus re-encodes information with new associations, influenced by current emotions and context. This process can strengthen memory, but also introduces errors. When a memory is recalled, it becomes malleable, engaging NMDA receptors involved in synaptic plasticity. These receptors help integrate new information, showing memory is an evolving narrative, not static snapshots. The belief that age inevitably erodes memory overlooks brain plasticity. While certain cognitive functions may slow, others can improve. A 2017 study from the University of Toronto found that older adults show increased bilateral brain activation. This compensatory mechanism aids memory performance. Neuroplasticity enables the brain to rewire itself, forming new connections even in later years. BDNF, a protein crucial for synaptic growth, increases with physical activity and cognitive training, enhancing memory capacity. Regular mental exercise can stimulate this growth factor, maintaining memory resilience beyond expected declines. Cortisol, the stress hormone, impacts your hippocampus, the memory hub. Within 30 minutes of stress, cortisol binds to receptors, reducing dendrite density in hippocampal neurons. This structural change decreases synaptic connectivity, impairing memory consolidation. A study from King's College London showed chronic stress could shrink the hippocampus by up to 14% over time. These reductions in dendrite complexity hinder cognitive flexibility. Yet, cortisol's effect isn't uniformly negative. Short bursts can enhance memory encoding by increasing alertness. The balance between acute and chronic stress determines the impact on memory pathways. Amygdala-prefrontal connectivity is your emotional control center. Stress amplifies amygdala activity, overriding prefrontal cortex functions. This shift amplifies emotional memories. Under stress, the amygdala hijacks resources from the prefrontal cortex, reducing rational decision-making. Studies using fMRI reveal increased amygdala activation correlates with decreased prefrontal engagement. This results in stronger emotional memory encoding while logical processing suffers. However, training in mindfulness can strengthen prefrontal amygdala connectivity, enhancing emotional regulation. Mindfulness has been shown to increase gray matter in both regions, improving memory and emotional balance. Dopamine signaling plays a critical role in memory reinforcement. In rewarding situations, dopamine is released, enhancing synaptic plasticity in the hippocampus. This neurotransmitter modulates long-term potentiation, a process fundamental to memory storage. Excessive dopamine, however, downregulates receptor sensitivity, reducing its effectiveness. A 2015 study from the University of California observed that overstimulation of dopamine pathways in the basal ganglia can impair memory retrieval. This highlights the importance of balanced dopamine levels to maintain optimal memory functions. Proper dopamine signaling encodes rewarding experiences into lasting memories. The basal ganglia are crucial for habit formation, impacting memory indirectly. They encode routines through a process called chunking, simplifying complex actions into seamless sequences. This habit encoding optimizes brain efficiency, freeing cognitive resources for other tasks. However, neuroimaging studies show excessive reliance on these routines can impair memory flexibility. If routine activities dominate, the prefrontal cortex's role in active memory retrieval diminishes. Breaking habitual patterns requires conscious effort, which re-engages the prefrontal cortex. This re-engagement enhances memory adaptability, encouraging the formation of new synaptic connections. Default Mode Network (DMN) activity reflects your brain's idle state. This network involves the medial prefrontal cortex, posterior cingulate cortex, and angular gyrus. Overactivity in the DMN is linked to mind wandering, which can disrupt memory processing. A 2014 study in the Journal of Neuroscience found excessive DMN activity correlates with decreased performance on memory tasks. Yet, the DMN also plays a role in autobiographical memory retrieval. Balancing DMN activity involves engaging in focused tasks like meditation, which has been shown to decrease DMN overactivity, thereby improving memory precision and recall. Chronic stress and acute stress have distinct effects on memory. Acute stress can enhance memory recall by heightening alertness and focus, while chronic stress depletes mental resources, leading to memory deficits. Chronic exposure to stress hormones shrinks the hippocampus and weakens synaptic connections. A 2018 study from Yale University found that prolonged stress reduces neural regeneration by 30%. This decline hampers the brain's ability to form new memories. Differentiating between these stress types is crucial for understanding and mitigating their long-term impacts on memory pathways. The self-help industry often promotes brain games for memory improvement. However, large-scale studies show these don't significantly enhance memory-related brain structures. Instead, physical exercise has a more profound impact, increasing hippocampal volume by up to 2% in older adults, as seen in a 2011 study by the University of Illinois. This increase is linked to elevated BDNF levels, fostering neuroplasticity. Unlike brain games, which may improve task-specific skills, exercise enhances overall cognitive function. These findings challenge popular beliefs, highlighting the need for evidence-based approaches in memory enhancement. Brain imaging studies contradict many popular psychology claims about memory. For instance, visualizing success, a common advice, may not solidify memory as assumed. Neuroimaging reveals that imagination and recall activate different neural pathways. A 2013 study found that visualization primarily engages the DMN, while active recall involves the prefrontal cortex and hippocampus. Relying on imagery alone may not enhance memory consolidation as effectively as engaging in activities that require active retrieval and application of information. Synaptic pruning in adolescence shapes memory capabilities. During this period, the brain eliminates excess neural connections, refining its network based on experience and learning. This process strengthens frequently used synapses, optimizing cognitive efficiency. However, imbalances in pruning can lead to memory and learning challenges. Studies show that excessive pruning may contribute to conditions like schizophrenia. Understanding synaptic pruning highlights how adolescent experiences can have long-term effects on memory architecture. Vagus nerve signaling offers insight into memory enhancement. This nerve modulates inflammation and mood, indirectly influencing memory processes. A 2020 study demonstrated that vagus nerve stimulation improved memory in Alzheimer's patients by promoting hippocampal neurogenesis. This stimulation increases norepinephrine release, boosting synaptic plasticity and memory retention. The therapeutic potential of targeting the vagus nerve suggests that non-traditional methods may offer new avenues for memory improvement, beyond conventional strategies.